All right, hold on. Here we go for our whirlwind tour of motion graphs. So my question for you is, are these two graphs that you see in the sections there the same? And the actual answer there is you can't really tell. I think a lot of people actually jump to the idea that motion graphs look the same, so they must be the same. But as you can see, if you change what's on the axes, it'll change whether they are the same or not. So on the left you have position versus time, and on the right you have velocity versus time. In the first section, there's like 3 sections in each graph. You can see the object moves away and then moves back and then moves away again in the x versus t graph. And that's different because in the velocity versus time graph, again, you have 3 sections, but what happens is the object is always moving away. It's just speeding up and then slowing down and then speeding up again. And so important to remember that the two graphs, if you look at the axes, they're very different graphs, even though they have the same shape. Now let's imagine that, again, I have the same graphs, but this time they are actually position versus time graphs, but I changed the units. And so on the left-hand side, you see meters versus seconds, and on the right-hand side, you see light years versus years. Obviously, those are different. Finally, the shape of the graph is also important as well. And so you can see in the red on the left, excuse me, that the relationship is linear, and on the right in black the relationship is exponential or polynomial. And so they're very different shapes, which means they have very different relationships. So what's important to remember about graphs when you analyze things? Anytime you go up against like an ACT style question, something like that, you want to ID the axes first. So what is it actually describing? ID the units, so you know what size we're talking about, and then ID the relationship, which is the shape of the graphs. So that's important. On the left-hand side, in the red there, that's what we did in Unit 1 with constant motion. And so we produced a bunch of graphs that had that linear relationship. In the right, in black there is what we're doing in Unit 2. And so you should expect to see some curved relationships between position and time in this unit. So now let's take a look at how I can use the position versus time graph to create a velocity versus time graph, so I can relate the two. Well, it's easy in Unit 1, right, because we had constant motion. So the object was changing its position in a constant way with respect to time, and so it's a nice horizontal line graph. So it makes it nice and easy for velocity versus time. In fact, we would say in that case that the velocity has no relationship with the time. However, in Unit 2, things get a little bit more complicated, and so we have to use this idea of how can we use the curve? Well, again, we're still talking about the slope. So if you look at the slope of the curved x versus t graph, you can see that the slope increases. And so just as a hint, without doing any math, you can see that the velocity must be increasing. And so that's what I used on the right-hand side. So in this case, let's go ahead and take a look at how I might actually determine the acceleration from a velocity versus time graph. And the answer is something that you've probably heard before, and that's the slope. The slope of the position versus time is the velocity, and the slope of the velocity versus time is the acceleration. I could also use the velocity versus time graph to go backwards to figure out how much the object has actually moved. And in other words, its displacement. And so to do that, I can show you that there is a little trick here, and that trick takes into account the idea of an average velocity. If you remember, the average velocity equation is equal to the displacement over the time. So I can solve that for the change in the velocity there. I can put the change in velocity in, and it will give me the relationship that I need. So the displacement is equal to 1/2 times the change in velocity times the time. Notice though that shape, if I extend a height down, an altitude down, I end up with the right triangle, and so I can use the same area equation to be able to figure out what the displacement is as well, if I wanted to find the area of a graph like that. In other words, that's really what they do in calculus, is slope analysis and area analysis for most of the year in calc. So if I want to graph accelerations in this class, I'm really only going to end up with 2 different kinds. So I'll either end up with the one on the left, where the acceleration is equal to 0. So the acceleration line just continues along the axis there, or some constant. And so for example, gravitation. The acceleration due to gravity is some negative constant. So we'll just graph it as a horizontal line. That's it. Thanks for watching.